Hi everyone, we are Jordi Masfarna and Albert Mazana, and today we are going to present our project about magnetic levitation. Before showing the experiment we did, we need to know what magnetic levitation or magnetic suspension is. Magnetic levitation, also called maglev, is a method by which an object is suspended with no support other than magnetic fields. We have to recall what magnetic field is. A good definition for magnetic field is the portion of space near a magnetic body or a current-carrying body in which the magnetic forces due to the body or current can be detected. The aim of this project was to see how it is possible to use magnetic force so as to reach the levitation. Our first objective was recreating these magnetic forces, and then we wanted to prove that magnetic force can actually counteract the gravitational force by making levitate different objects. To recreate levitation, we will use a magnet and an electromagnet, which will be a copper coil. To do this experiment, we will need the following material: a thin wire of enameled copper, a ring-shaped ferrite magnet of 8 cm diameter, a 1 ampere and 12 volt electrical transformer, a platform on which we will allocate the magnet, thread, sandpaper, a voltmeter, an auxiliary object that resembles a cylinder, sticky tape, and we also used a stapler. As it is not possible to buy a copper coil, we will have to do it ourselves. To do so, we take the thin wire of enameled copper and we turn it 60 times over the auxiliary object. Once we have done this, we join the 60 turns of copper wire with sticky tape so that they stay together forming a coil. This is how the coil should be once we have joined the wires with sticky tape. As the copper wire is enameled, we need to sand the endings with sandpaper so that the current can flow through it. Then we have to check the conductivity of the coil. We can see that the ends which have been sanded are conductive. Next step is to tie the coil with thread to a solid surface, such as paperboard. First time we did the experiment, we tied the coil to a sheet of paper, but the magnetic force was strong enough to lift the ends of the paper. At this point, it's time to connect the coil to electricity. To do this, we first need to make sure that the voltage and intensity in the electric transformer are the ones we need, so we measure both things with the voltmeter. When connecting the coil to electricity, we can see that yes, it levitates. But why does this happen?
This picture will help you understand how the coil and the magnet behave. The magnet on the bottom part is creating a magnetic field itself. Then we make the current flow through the coil and it will also create a magnetic field, but on the opposite direction. Consequently, they will behave as two magnets that are facing each other with the same polarity, so they will be repelled.
Now we turn the magnet upside down to see what happens.
We have seen how a coil and a magnet behave when the current is also participating on the equation. But what will happen if current flows in the other way? By intuition, we can clearly see that both objects will be attracted, like the North and the South Pole. We also can test the forces created by the magnetic field. For example, we can play around with it by putting objects over the coil and see how it reacts. In our case, we use a paper sheet that acts as a thin platform, and over it we put a wooden die, or just by only using a little box. One of the issues we've had during the development of this project was making the coil with less radius than the magnet and not tightening the auxiliary threads enough. When the coil was placed just over the magnet and we switched on the transformer, the coil didn't behave as expected. The part of the coil which was slightly closer to the exterior radius of the magnet was lifted up because the magnetic field was much intense. On the contrary, the part closer to the interior radius was completely tracked towards the magnet. That has an explanation, which is the following. The part of the coil that was lifted up made the other part drag towards the empty center of the magnet. In that situation, the magnetic field created all over the coil in the upper part didn't play any role initially. Indeed, it took part in this specific situation, producing an attraction between the coil and the magnet like a North Pole and a South Pole do.
Now that we've seen the theoretical concepts and principles related to levitation, it's time to check if levitation is practical in our lives. For example, when shops are interested in selling a product, they may use magnetic levitation so as to allocate the object on a platform that levitates and this way catch consumers' attention. Another application that has to do with football is using the magnetic force created by two magnets so as to make the ball kind of float and impress the public. This can be seen in some special football matches before the professional players enter the pitch.
Another interesting example, in this case applied in the industrial field, is the magnetic levitation, specifically the one that has to do with trains. This kind of train is known as maglev train, from the term magnetic levitation, and it was developed in Japan in the 90s and tested in many countries because of the fact that it can speed up to 600 km per hour. It is clear that it makes a huge difference in terms of the way of commuting to work between long distances, among others. But the cost of the track, the guideway, the impossibility of transporting huge weights because it requires a lot of energy, and the train itself makes this project unrealistic for some countries. The train contains superconductive electromagnets, and the track is full of magnets as well. When stopped, the train rests on rubber wheels. To begin motion, the train moves forward slowly on these wheels, allowing the magnets beneath the train to interact with those of the guideway. That is achieved when alternating current flows to the bottom part of the train, just over the track, which produces a continuous change of polarity of the train magnets that will be attracted or repelled with the ones located in the guideway to propulse itself. In order to keep the train lifted during the transportation, a set of magnets with a certain polarity are located along the track and beneath the train with the same polarity.
That's all for today. Thanks for watching and see you in our next video.